Hello everyone and welcome back. In this video, I'm going to be discussing a little bit about vector valued functions. Now, if you're wondering what a vector valued function is, as the name suggests, it's basically a function that describes the components of a vector. So basically, each component of a vector is a function itself. So if you're in three-dimensional, let's say, physics problems, and you're trying to describe the position vector of a particle that's moving through space, you need three components, x, y, and z. Now, the goal, though, is that we have functions that describe that x, y, and z basically explicitly. We want to find some kind of parameterization so that it brings the number of degrees of freedom from 3 down to 1. So we basically only want to have, let's say, one running parameter called t that has all three x, y, and z components evolve. Similarly, if you're in the 10-dimensional space and you have 10 degrees of freedom, you want to again find a way to parameterize and dumb down in a way the dimensions back to one dimension. So, of course, that is a lot more complicated, but if you're in 3D, which is usually where we're in when we're doing such problems, the job becomes a lot simpler. So there are 4 kinds of parameterizations that you need to keep in mind based on the form of the equation that you have at hand. There's probably more if you look deeper into math for different kinds of weird functions, but we're not going to look too much, again, in depth. We're only going to go up to Calc 2, essentially depth here. So the two that you encounter in Calc 2, certainly, will be the explicit function form and the circular form. The ones that you might encounter in Calc 2 is the elliptical form, and ones that you're going to encounter probably in a physics curriculum, and rarely, will be the hyperbolic form. So how does this work? Let's see at the ones that are relevant here for Calc 2. Let's say right now that you have an explicit function here, as you can see, y of x, right? And this function here clearly is some kind of parabola shifted by some amount. So it's a parabola shifted by some amount here up. Fair enough. And we can see that if I want right now to describe the position of a particle that's moving along this parabola at a certain point, let's say here, what do I have to do to find the components of this vector r right now? Well, again, we would love to express the x component right now as itself because it is the independent variable. It is what the y function absorbs to give you an output. So we'd like to leave that alone. And then the y component over here, as you can see, will be dictated by the value of the function actually at that point. So it's going to be basically y of x, and whatever x you're feeding this y, it's going to give you out an output for that y component of your r vector. So if you were to write this vector right now, it would look like this. It would look like x hat plus y of x y hat, or in, again, bracket form, it would look like this, x comma y of x, essentially. So typically, though, we don't let the variables be x, y, and z if we are parameterizing in terms of them. We always let the parameterization variable be called t for, again, communication in Calc 2. We notice again that the independent variable here is always going to be the parameterization. So this time here it's the x. So again, we just call x the parameterization variable because that's who it is. And then we get explicitly what r of t here is going to be, namely t and then y of t over here. And then y of t, in our case, in a little example I've given with a parabola, you can see over here, this is the equation in terms of x. If we change x to t, this is nothing more than t comma minus t squared plus b. And that again is the parameterization specifically pertaining now to the example that we have on the left on the image. Okay. So now that we've got that down, we're going to try it, of course, in some examples. Let's look at the circular form 1 sec. So the circular form, we know that the equation of a circle is x squared plus y squared equals to some kind of r. And I can manipulate this a little bit to write it in terms of this. We can write it as x squared over r squared plus y squared over r squared is basically equal to 1. We just divided both sides here by r squared. And I'm thinking to myself, what kind of equation could look similar in form here, but only involve one parameter, one running parameter? So I can dumb this down from 2 variables to 1. And the truth is, we have an identity that does this. We have cos squared of t plus sine squared of t is equal to 1. And if you match here terms by comparison, you can see what we can set each of these above to what terms we can set them below. Essentially, x squared over r squared, we can set it equal to cos squared of t, and y squared over r squared, we can set it equal to sine squared of t. And now, this invites, of course, a rearrangement, and you can see that x is basically going to be r cos of t, while y is going to be r sine of t. And those are basically the parameterizations that we would use if we had an equation of this form that we needed to work with. Okay, so this is again very common. A little bit more rare is the elliptical form, which again, if we know the equation of an ellipse, it's x squared over some constant a squared plus y squared over some constant b squared is equal to essentially 1. And the same equation that we wrote down before will help us do the trick here of parameterizing such a form. And we can see how we can basically match terms again over here, the same way that we did before, essentially. So that x squared over a squared is again equal to cos squared of t, and then y squared over b squared is sine squared of t. Now I can go ahead and resolve for what x needs to be here. It just needs to be a cos of t, and then y here needs to be b sine of t. And yes, this is the parameterization of an equation of this form, regardless what a and b are. So now we have the 3 basic parameterizations, as you can see over here. And now we're ready to move on to doing some examples. So let's put them to the test. We want here to define a vector-valued function for the intersection of the following geometrical objects. We have in the first one, as you can see here, a plane, x plus y equals 4, and another plane here, x plus y plus z is equal to 3. So what are my moves here? Okay, first, I'd probably check if there are 2 things here that look exactly the same, namely the y's and the x's. I get to choose here. I think I'll choose to go with the y over here and isolate it in equation 1. So I'll have y here is equal to 4 minus x. Notice that I'm writing the y explicitly as a function of x right now. Explicitly. And then for number 2, I can do the same thing, but this time around, for equation number 2, I'm not going to write y explicitly. It's going to involve a z here, as you can see. So before I get to what the y will turn out to be, let's take care right now of what maybe the z or the x are going to turn out to be. How do I find what's going to happen? Well, I can eliminate the y right now dependency if I set 1 equal to 2. That will leave me with 4 minus x equals 3 minus x minus z. And then over here, I can kill the x's immediately. And then over here, we have essentially 4 minus 3. So 1 equals to negative z, or z is equal to negative 1. And that is one of our 3 parameters right now. We have to fill in what x, y, and z are going to be in our final answer over here, if you recall. So we have here 3 components that we're waiting for to go into this. And we just found that the third one is going to be negative 1. Very good. What are the other two? Well, for the other two right now, since z is not going to do anything, it's not going to be a running independent variable. It's just -1 right now, its value. So that's where the intersection again is happening. Across z equals -1. The z never changes during the intersection of the two planes. So what is going to happen then for the other two? I can look at this and recall that I could write a parameterization right now of the two components, x and y, like this. Because again, x is the independent variable right now that I vary, and y is the guy that is dependent on x. So I can write my r of x with an x component equal to the independent variable and a y component equal to the dependent variable. So again over here, if I plugged in what y of x is, it would be 4 minus x. And then if I let x equal to t, because really x is the actual independent variable in the parameterization. If I let that happen, then r of t for the two components here, the x and the y, is going to be t and 4 minus t. And that's exactly what I fill in for the last two components here. So the x is going to be, again, t, and the y is going to be 4 minus t. And there we go. So there's a chance you did this in the opposite way. If you're solving yourselves and you solved for x as a function of y, it doesn't matter. All that would happen here is that you would flip these answers, and it's completely okay if you do so. You get the exact same kind of behavior. You just have it happen mirrored instead of having it, again, the t behavior in the x direction, you have it in the y direction. It's just mirroring the two axes, which is not a big deal. Okay, what about the two planes that we see here? What can we do with them? Again, I'm looking for something that is identical between the two equations here, the 1 and the 2. And it's the z. So I'm going to go ahead and isolate for z in equation 1, giving me here a function of z as, a function z as a function of x. And I'm going to have here 2 minus x for that. And from the second equation, I'm going to have z as a function of y, and it's going to be 2 minus y. So again, I can kill the z dependency by equating the two equations. And we have here that 2 minus x is equal to 2 minus y. Essentially, the 2's here go away. Minus x is equal to minus y, or x is equal to y. I would like to write this, though, as y is equal to x, because I want to emphasize again that we have explicitly written down y as a function of x. So you guess what's going to happen here. We're going to have a little r of t for the two components y and x. X is going to be the independent variable again, so it's going to be the actual parameterization of this problem. And y is going to be depending on x. So if we again set that x is the parameterization here, we get the first two components of our answer. So the x component is going to turn into a t, and the y component, well, since it's basically, again, y is equal to x, we will have another t for it right there. And the first two components of our final answer have been discovered. They are t and t respectively. So what's the z1? The z1 over here, you can see, it's either 2 minus x or 2 minus y. But both are equal to t, as you can see from the work that we did earlier. So basically z is going to be 2 minus t, and that's the conclusion. Done and done. So that's example 2. Let's look at example 3, which is a sphere intersecting here with another little plane, z is equal to 2. So what do we do here? Well, first of all, we can't do much unless we kill some kind of dependency. If right now I actually go in and plug 2 into 1, equation 2 into 1, I should say. What basically happens is we can actually work on the x and y independently right now through this equation. Okay, so we have x squared plus y squared equals to now If we move the 4 on the other side, 1. And this is exactly a circular form, which we know how to deal. We know that x is going to end up being r cos of t, and y here is going to end up being r sine of t. Okay, but what is the r in this case? Well, we can see that the dividers here of both x and y are literally 1, so that's what we plug in. And essentially x is equal to cos of t, while y is equal to sine of t, and we've got 2 of our 3 components for the vector valued function, cos of t and sine of t. We only need to find the last one. But the last one, for the z here, we've been explicitly given this z. It will always be 2 during this intersection. So that's what we put down. I mean, if you plug back in these guys back into here, you could figure out that z again is going to be equal to 2 that way too. But, you know, if we look around and use our eyes, we're going to see that z existed here as 2 all along. So we don't have to do any extra work. And that's our answer. Fourth example here has a cylinder intersecting with a plane. We'll call the equations again 1 and 2. What I see again, the cylinder is basically, if you take a look, it's a circular form where the r again that we're dividing these guys by is just 1. So we recall that x, when we see circular forms, x of t is going to be r cos of t, y of t is going to be r sine of t. This time again, though, the r value is equal to 1. So they're exactly cosine and sine, respectively. And we've got immediately 2 out of our 3 components here again. So what is the third one? Well, the third one over here, we need a little more work to do. We can look at equation 2, because we already looked at equation 1. Equation 2 here says that z, we can isolate for z because that's what I'm looking for anyways. Z as a function of x is equal to 1 minus x. Well, we already know though from our previous work that x is literally cos of t. So our answer for z is 1 minus cos of t. We write it down and we are golden. We are ready to go. That is how quickly you can do some of these questions if you know what you're looking for. So the last one over here is a paraboloid, equation 1, and another little plane intersecting. So what I can do for those, essentially, I basically I need to kill a dependency on the top equation. So one way I can do that is plugging 2 into 1, and that way here I can get 3 squared plus y squared. Now remember, z right now looks like it is explicitly written in terms of y. And we all know what that means. That means that r, well, in this case, it's going to be r of y first, and then it's going to become r of t. R of y is going to be essentially the independent variable here is going to be y. Secretly, that's going to be our parameterization then. So y is going to be the independent variable. Z of y is going to be the dependent variable. And then we can put in what z of y actually is, 9 plus y squared. And then, of course, we do let people know that we're using y as the parameterization, in which case we get here r of t now. We get the 2 components, y and z, written in terms of the parameterization. So t and 9 plus t squared. And this fills up 2 out of 3 components again for the overall vector valued function. We're only missing the x right now. Okay, so what is our x? Well, our x, again, if you see, was explicitly given earlier in the question. We don't have to go and solve for it. And so that's exactly what we put in its position here. It's going to be a constant. And that is our answer for this last question on the paraboloid and the plane. So, again, not too hard once we find the pattern. Some of them are a little bit hard because we need to use our brain a little bit and think who is the actual independent variable in all of this? Like in the two equations that we're merging right now, who is the actual independent variable? And that guy is actually going to be the parameterization. Sometimes we get explicit numbers to pop out. For example, here we got an explicit number for z. That means it doesn't depend on any t. We'll put it in as is. Some other times we got over here equations here for y in terms of x, where x is the independent variable, and we've judged that. So essentially we replace x by t, and y here would be 4 minus t. You got the other two components and you're good to go. So practice this and you should be golden. Now I hope again that the derivation of the parameterizations up here and the actual application examples helped you understand a little bit how to parameterize vector valued functions. If so, consider subscribing. And again, thanks for watching.